Thank you, Audrey. Welcome, everybody, for this Family Research or Family Scientist 2024 symposium. I'd like to thank the ELA International team, particularly Audrey Boyer, who is our new person in charge of research. She replaces Elly Villa, for those of you who knew her. And I'd also like to thank Jean-Luc Party, is the international secretary, with the French team with Hervé Perra, who is in charge of the technical and IT-related issues, and the whole interpreting translation coordinated by Isabelle Bousset, who chairs the company called Pourparler, with whom we're collaborating, and we've been collaborating for several years. And the interpreters are kindly asking us to speak clearly and not too fast, so that the interpreters are in a position to hear clearly everything being said. This is a message for the speakers. I would also like to thank wholeheartedly, from the bottom of my heart, the speakers who have agreed to take the floor today. They're dedicating some time to us, but they also dedicate time throughout the year to the research, and the care they provide for the patients is very important. So I really would like to thank them for this. And you know, we don't just want to thank them. For years now, we've been supporting research on leukodystrophy. I'll give you an example. In 2023, ELA International dedicated 1.3 million euros to the research regarding 7 ultra-rare forms of leukodystrophy, of which 4 are new, so that we don't need any kind of leukodystrophy not being taken care of. And we're going to renew this funding in 2024. Ever since ELA International was created in 2015, we have studied 20 forms of leukodystrophy. You know, we've increased the knowledge on these forms. And ELA France was created in 1992, and 50 million euros have been invested in medical research. And that is the equivalent of 571 programs. And ELA is the number one among the associations providing funding for research on leukodystrophies. 2023, we also created an international ethics committee. ELA International decided to set up this ethics committee to think and debate about main issues such as neonatal leukodystrophy screening, access to new therapies, not always easy, or also how to better associate the patients to clinical research. Now, when we created this ethics committee, we wanted to identify the values that the association may rely on to protect the patients and the family's interests. There are 11 members in the committee coming from different backgrounds, family representatives of patient parents from several countries, ethics experts, legal experts, human science experts, pharma company or laboratory managers, and researchers. And this means that we have a balanced way of debating sessions, and Professor Grégoire Moutel chairs the sessions, and he's an expert working for the Caen Teaching Hospital in France. Let's look at the first subject that the committee looked into, neonatal leukodystrophy screening. As you probably know, new therapies that have been cleared by the drugs agencies, both in Europe and the US, are now arriving on the market. Skyzona for cerebral adrenal leukodystrophy, or Limeldi for a gene therapy for metachromatic leukodystrophy. However, these therapies are not necessarily accessible to all patients, either because they're not being reimbursed by the local social security, or because the disease is too far advanced for the therapy to be efficient. And for the therapy to be efficacious, it must be administered soon enough, early enough, even before the first symptoms appear, which means that we have to screen the babies at birth to know that they suffer from the disease, because there is a very limited therapeutic window. So a solution for leukodystrophies would be neonatal screening, However, obtaining that all babies are screened within countries is not obvious. It's not a matter of cost because it's not very expensive, and honestly, it saves lives. The ethics committee has looked into this issue throughout the 2023. We've spent hours discussing. But we also listened to experts giving an audit, or we looked at papers and publications, and the committee gave a favorable opinion for neonatal screening of beta-leukodystrophies and adrenal leukodystrophy. But, things are moving forward, and we now have a good rationale, good arguments that we can submit to the health authorities in France or in other countries in Europe, with the hope, obviously, of obtaining the necessary clearance and authorization to perform screening at birth. We are fully aware that this is very time-consuming, but if we want things to change, we have to get together and work on it. We have to be committed. Now, the first thing that is accessible to all those listening today and others, would be to start by registering to our LeucoConnect platform. This is something you can do if you want to do something on your own level. We created the ELA International structure in 2015, and we had two aims: to pool together our funding, to bring together the patients from all over the world, and the researchers will agree that this is the best way to accelerate therapy discovery. And this is the reason why we created the LeucoConnect, an international platform for study and clinical research. And all the families are brought together on this platform. So please do not refrain. You can register on the site www.leuconnect.connect. It is time, honestly, it is high time to register and join us. We will be stronger together to ensure that we find new therapeutic solutions. Now, before I give the floor to Raoul Esteves, who will also be chairing the session, and I would like to thank him for all the years that he's been contributing to the scientific committee and council's work. But before I give him the floor, I would like to repeat how much I respect and admire the patients, the parents whose children are affected, the families, because your testimonies are essential. And I would like to thank you and show my admiration for your resilience, because you're in the first line. The patient's voice is spoken through you. You are Ella's strength in the fight against leukodystrophies. You're irreplaceable, and you have to play an essential role within this organization. Thank you very much for your attention. Thank you to all the speakers who will be delivering a presentation today, and I wish you a fruitful 2024 symposium and a
Thank you so much for the introduction, Raoul. I hope I share my screen. Correct?
Yes.
Okay. Thank you so much. And good afternoon, ladies and gentlemen. It's a pleasure for me to give an update on Vanishing White Matter, also called CASH. And if there's something you cannot hear me well, because I tend to have a little bit of a soft voice, let me know. So this is my funding. It causes no conflict of interest. And this is, we are holding a patent for the therapeutic effects of guanabana's treatment in Vanishing White Matter in the USA and the EU. And we have an orphan designation for guanabans. I'm a consultant on the subject of Vanishing White Matter trial development for Calico and a co-investigator for the Alexander disease trial for EONUS. So these are the subjects I would like to cover this afternoon. I would like to start off with a brief overview on Vanishing White Matter, disease mechanisms and therapy targets. And this might be a little bit of a repetition for families who heard me before. But if there are new families, I want everybody to be on the same page and understand what I'm talking about. Then I'll give an update on the guanabana's trial, which is in part funded by ELA. I'll also announce the EIF2B activator trials, and I'll say something about the International Vanishing White Matter Registry. So, Vanishing White Matter can have an onset at any age. The most common form of the disease is also called classic vanishing white matter and has an onset in early childhood, mostly between 2 and 6. And it's characterized by chronic motor decline, mostly ataxia, so coordination problems, unstable gait, losing gait, and also difficulty using the hands, less obvious cognitive decline, and epilepsy. Sorry for my clock, it's a little bit loud. And also epilepsy, but typically epilepsy is not very bad. In addition, on top of the chronic decline, there are episodes of major decline, which are typically provoked by physical stresses. So not psychological stresses, but physical stresses like infections, fever, and minor head trauma. Also major surgery may do it. And so what happens is, like a child has a common cold with a little bit of fever, then starts to decline and cannot walk anymore, lies on the couch, it becomes has a lowered consciousness and may lapse into coma and may end in the intensive care unit for unknown reasons. This may be followed by partial or complete recovery, but also patients may die during an episode. Vanishing white matter with early onset is actually a rather bad disease, and patients die after a variable number of years, and sometimes they live decades. Then we have very early onset vanishing white matter. So some patients are already symptomatic at birth, and some develop signs in the first year of life, and then they have a generalized encephalopathy. So they have very little development, they regress soon, they may have severe epilepsy. Some children are very irritable and they die within months. I have not seen any patient survive more than 2 years. And then we have late onset vanishing white matter. The latest onset I know of is around 68, 67, 68. And the late onset vanishing white matter with adult onset is characterized by mostly cognitive decline and behavioral changes, and later and less striking motor decline. It's a much slower disease, much more variable, fewer stress-provoked episodes of rapid decline, and these patients typically live for decades. So what you can see is that disease onset is really a strong predictor of the disease course regarding clinical signs and also rate of progression. The disease course is more variable with later onset. So the early onset cases have a more share a common disease course, but later the disease course is highly variable. We started to collect data on vanishing white matter patients in 2004, and in 2017 Elaine Hamilton did a natural history study. At that time we had around 300 patients and worldwide, and we divided the patients according to age of onset, and I just explained why we do that. So onset below the age of 1, onset between 1 and 2, 2 and 4, 4 and 8, 8 and 18, and from the age of 18 on. These are Kaplan-Meier plots. This is about survival, this is about walking, and this is about cognition. So what you can see is the later the onset, the longer patients live, the longer they walk, and the longer their cognition is preserved. If you then plot on the x-axis disease duration, then the Kaplan-Meier curves are about speed of the disease, and what you can see is that early onset is extremely rapid, and then with somewhat later onset it starts to be a little bit slower, and then the later onset cases are the slowest so they have the longer survival. Loss of ambulation is latest. The only exception is cognition, which is earliest in adult onset vanishing white matter. These are the patient numbers according to age of onset, and what you can see is that by far most patients have an onset between 2 and 6. And so this is what we call the classic disease. 2/3 of the patients have an onset below 6. If you look at patients that are living now, the picture is different, because many young patients die soon, so the living patients are typically older. So 2/3 of the living patients are 16 years or older. In the Netherlands, only university hospitals do genetic analysis, and my lab was the only one offering genetic analysis for vanishing white matter for a long time. And so we pretty much knew all patients in the Netherlands. So we know incidence in the Netherlands. It's approximately 1 in 100,000 live births, and the prevalence is approximately 1.3 per million. And there's no reason to assume that it's different elsewhere. It's not that we have a lot of consanguinity or big founder effects in the Netherlands. Vanishing white matter is a genetic disease, and the genetic defect affects a factor called EIF2B. Now, EIF2B is here, and it's central in the translation of DNA into proteins. So it's conditional for the production of proteins. That means that it's also conditional for life. The second function it has is in the integrated stress response. This is a cell stress response, and this is about the physical stresses I was talking about, like fever, infection. There are others like amino acid starvation. And during those stresses, protein synthesis needs to be reduced. And one reason is the protein synthesis takes a lot of energy, and during stress, the cell needs to survive and recover, so it doesn't need to make new proteins. And also new proteins may be malfolded, and so protein synthesis needs to be shut down during stress conditions. That's done by EIF2B. In vanishing white matter, the activity of EIF2B is decreased. It's never zero. Patients need a remaining activity. If it would be zero, there would be no life. So we have a remaining activity of EIF2B, and I'm convinced that the lower the activity of EIF2B, the more severe the disease is. Now here we are talking about the cell stress response, the integrated stress response. And it's important to realize that this stress response is crucial. We all have it. We all have it to help us survive febrile infections or other stress conditions. And so it's a beneficial response. And you see in the middle of the beneficial response, there's EIF2B. I'll explain to you what happens. Here are the stresses: infection, reactive oxygen species, heat, amino acid starvation, unfolded or misfolded proteins. Those are the stressors. They all do the same thing. They activate an enzyme that then phosphorylates EIF2. EIF2 tightly binds EIF2B and in this way inactivates it. Then there are two effects. One is general protein synthesis goes down. I explained that to you. And the second thing is ATF4 is activated. And this releases the ATF4 transcription response. With many factors, hundreds of proteins are activated. And this transcription response is going to determine whether the cell is going to recover or the cell is going to die. Of course, on a stress response, there needs to be a break. And the break is GAT34. This is a negative feedback loop that leads to dephosphorylation of EIF2. And then when the stresses are gone, everything goes back to normal. So GAT34 is the break of the system. Now, in vanishing white matter, EIF2B activity is always down. We have never found that general protein synthesis is compromised. And I think that the remaining activity of EIF2B is a guarantee that the protein synthesis is still fine. But the ATF4 transcription response is always activated. So in vanishing white matter patients, it's not just stress, but in all days of their life, their ATF4 transcription response is activated. And we have evidence that this is the central part of the disease mechanisms in vanishing white matter. So they have a continuous abnormal activation of the ISR below EIF2B in brain cells. And we've also been able to find that the higher this response is activated, the more severe the disease is. So there's a relationship with how bad the disease is and how active this ATF4 transcription response is. It's not that I now understand everything, but in clinic we don't have to the time to understand everything. We already need to think about therapy when we only understand part of it. So therapeutic options. One is avoid stress. Obviously, the stressors that are here are also the stressors that make vanishing white matter patients go into an acute decline. So from 2001 on, when we found the genes, we are saying avoid those stressors. And like avoid febrile infections, avoid fever, avoid head trauma. And it makes the disease, I would say, calmer. So the big episodes are gone, but the chronic decline is still there. So we need to do more. Then obviously, an obvious target would be EIF2B. As I said, it has always remaining activity. So can we activate it? And the second thing I would think about, or the third thing actually, is can we work on GAT34, this break in the system? Can we make that change so that it also indirectly leads to an activation of EIF2B? Or, that's what we also have been looking at, can we modulate other compounds, other components of the AT4 transcription response? I'll now show you two effects. First, working on the GAT34 feedback loop, the break in the system. There's an old drug, Quanabens, and it's an alpha-2 adrenergic antihypertensive drug. It was developed in the 70s and entered the market in the 80s. It's just an oral medication. You could buy tablets or capsules, and it's FDA approved. It's safe. There's no long-term side effects. It's only no longer used. It's not very effective on reducing the hypertension. What was known already that it also impacts the ISR through the GAT34 feedback loop, thus activating EIF2B indirectly. We have mice with vanishing white matter, and they replicate the disease of humans. So they have also white matter disease, they have abnormal ISR activation, and so they replicate the disease, and we thought, what if we would treat these mice with Quanabens? And we did that, and it decreases ISR activation, it improves neuropathology, and it improves motor performance. Let's show it. We have a catwalk in Amsterdam on which we can have the mice walk, and we can visualize it, and this is the normal mouse. We slow this a lot because normal mice don't walk slowly like this. This is a normal mouse. This is a vanishing white matter mouse, and you can see it's way slower. It's also very unstable, so it has gait ataxia. It's leaning against the wall for stability. It uses its tail, and but you can see it's actually pitiful. Then we treat it, vanishing white matter mice with Quanabens. And I think you can see how much the gait is improved. So this is an old drug, so we can just use it. And on the basis of this, we initiated a phase 1-2 trial, and phase 1 means it's about safety, and that was done because Quanabens had never been used in young children, and that was what we are going to do. Phase 2 looks already at efficacy. So we have an international monocenter trial in Amsterdam. It's open label, so all patients are treated, and we use untreated historical controls from the registry. Early onset vanishing white matter is such a bad disease that I thought it was unethical to have placebo controls. So we used the controls from the registry. We were allowed 30 to 40 patients with early onset disease, onset below 6, and they still would have to walk. They could use a little bit of support, but not much. So we went for these patients because the younger patients have a more predictable disease course. And that makes that matching with historical controls is much easier than with older patients. So we can really avoid the placebo group. They have a faster disease, so that the trial can be smaller and shorter. And we go for earlier the disease so that they still ambulant patients to avoid too much irreversible brain damage. Because if you test a drug in end-stage disease, it might be that you don't find an effect because the brain damage is irreversible, not because the drug is not working. That's the reason why you go for early in the disease course. Our primary outcome is safety. I explained that. The secondary outcome is time to loss of ambulation. We started in May 2021 and the end of inclusion is May 2024. So that's in just 1.5 months. The total trial duration will be 4 years, so it will be still a year, and all patients stay in the trial until the end. We did an interim analysis. We did that in the fall of last year, and we then had 19 patients that already had a follow-up of 1 or 2 years. Concerning safety, the long-term safety is known, but on the short term, patients have alpha-2 adrenergic side effects. So initially, they have drowsiness, they may have hyperactivity, some patients have hallucinations, but these side effects are dose-dependent and wear off. So we mostly see them initially when patients are for a couple of weeks in Amsterdam to get titrated to the right dose. Then we see the side effects and then they are typically also gone, then they go home. For the matching, for the control group, each trial patient was matched with 2 untreated vanishing white matter registry patients. And we matched them for age of onset because that determines the disease course. The controls should meet the trial criteria at a similar disease duration as the patient when entering the Guanabens trial, so should also be still ambulant at the same disease duration. The untreated controls should have follow-up information, and if multiple patients would be available, then we chose the 2 most recent patients. And the good thing is that there is a difference between Guanabens arm and the untreated historical control, and you can see already the p-value is going to be significant. So there is a significant effect of Guanabens. We are preparing for the future. So as I said, we have a patent granted in the USA and the EU. The patent in Canada is pending. We have an orphan designation. We are currently working on getting the money there for the long-term extension of the trial because the trial patients need to be continued on the drug, and we want to go for registration and making the drug available at a price that's as low as possible, because I want to provide something to treat the patient with in any area of the world, also in very poor countries. Then how about eIF2B activators? Those are chemical compounds directly increasing eIF2B activity, and they have been found by compound screening. They're also just capsules for oral use, and they have been tested. They have a good short and medium-term safety. Of course, we don't know the long-term safety yet. No patient has been treated for 10 years or 20 years. Currently, the drug is tried in ALS patients, and I think the trial duration in ALS is already 2 years, and there are no major side effects. So there's a good medium-term safety. We also tried eIF2B activators in our vanishing white matter mice and saw exactly the same as Guanabens. They decrease ISR activation, improve neuropathology and motor performance. And I'd like to show it to you again. These movies are a little bit faster. So this is again the normal mouse. This is the vanishing white matter mouse. You can see again how unstable the mouse is and how much he needs stabilization against the wall. And then this is the vanishing white matter mouse with an eIF2B activator. So that also works. Danico is the first company that had the eIF2B activator and the first company to start a trial in vanishing white matter. The phase 1/2 trial is already up and running. It's a safety trial and a PK/PD trial. It's open label. It already started in Utah in June 2023, and we are the second center to open, so we just screened our first patient on March 26. We will have the maximum of 8 patients in Amsterdam, 3 adults, 2 between 2 and 18, and 2 or 3 between 6 and 12, and the patients are non-ambulant or have a low IQ. And that is to make sure that there's no overlap with the next trial that's going to start by the end of the year. That's the efficacy trial. And Amsterdam will start first. We will also be the PI center worldwide. And it will be placebo controlled because that's the best way to show efficacy. So 2 patients get treated, 1 patient will be a control. And patients need to be ambulant and the IQ needs to be above 50. And you can see that the criteria for the phase 1-2 trial have been made to make that there's no overlap between the 2 trials. The primary outcome measure will be defined, so which will be about mostly behavioral problems. There will be a separate trial for very young patients. It will be open label with historical controls from the Vanishing White Matter registry we have, and they do not need to be ambulant. But the criteria still will be defined. So now the registry. We have for 20 years a registry on Vanishing White Matter in Amsterdam. Currently it includes 450 patients and it's worldwide. And it's based in Amsterdam, but it's not our registry. It's an international registry and it's governed by the International Consortium of Clinical Vanishing White Matter Experts and Patient Advocates. So we are setting this up that this is the body to make decisions on who is going to get what information. It uses Castor, a cloud-based secure system that can capture and integrate data from any source. It's available in many languages, including French. I don't speak French, but the database speaks French. It follows the guidelines of FDA and EMA to be future-proof. It allows international sharing of data with other researchers and industries. It's suitable for different studies, like natural history studies, impact of disease studies. It's suitable, this is very important, for providing historical control information for trials. And it's also suitable for sharing results of trials. So I would like to say it's really crucial for patients with Vanishing White Matter or CASH to be in the registry, because we'll use the registry to identify patients who might be eligible for trials. And the registry is also used to reduce the number of patients on placebo or to avoid the placebo arm at all. I've been talking with Audrey about Look Connect, and Audrey is willing to help me, us I should say, find patients eligible for trials, but then they still need to register in the registry. So this is the email address that anybody can use who has a question on the registry or wants their patient or son or daughter or spouse entered in the registry. I was talking about the Vanishing White Matter Consortium. So, as I said, we have a problem. We have multiple therapeutic possibilities for an ultra-rare disease. And we envision multiple parallel trials competing for each other, and each could be underpowered. We don't want that. So the aim of the consortium is to facilitate therapy development and guide trials for Vanishing White Matter cash. So we want to test multiple drugs in overlapping or parallel trials, which are adequately powered, and we want to share the placebo controls. If trials share placebo controls, they can each use the same control for the different trials. And then the number of patients in the placebo group can be reduced or minimized. So what we did is we developed a core protocol, which can be shared by all trials. And the Calico trial is already using the core protocol. So the first to enter is already using it. And these are the members: Joshua Bonkowski from Salt Lake City, Ali Fatemi from Baltimore, Adeline van der Ver from Philadelphia, Ingeborg Kregelo-Mann from Tübingen, Enrico Bertini from Rome, Geneviève Bernard from Montreal, and Paulo Scobie de Souza from Brazil, and Nicole Wolf from Amsterdam. And you see, we chose them to cover a big part of the world. This is the Vanishing White Matter team in Amsterdam. So this is the trial team. And are the people working in the lab. These are people also working on biomarkers, pharmacists. And then, of course, I'm now entering in a whole new era of drug registration. So I need a business developer and platform medicine for society that helps us determine a reasonable price. And these are the PhD students. Thank you so much for your attention.
Yeah.
Okay, thank you so much.
Thank you very much, Marjo. Very nice talk. So we move to the next speaker, which is Elly HOL, also from the Netherlands, from Utrecht, no? And she will talk about Alexander disease, why research is crucial to understand the disease and to work towards a cure. Thank you, Elly.
Okay, thank you, Raoul. I'm really happy to be here and to talk about the research that we did over the last years in a European consortium that was all focused on Alexander disease. I hope you can all hear me well, and if not, just let me know and I can adjust. So Alexander disease is a rare disorder. 1 in 2.7 million can get the disease. It's also a white matter disorder, so people get problems in their white matter areas, as you can see here on an MRI. The clinical features are seizures, a larger head, and spasticity. And if you want to understand disease, very often people would like to go and look into the cells under the microscope, and what is known already for a very long time and was first described by Alexander in 1949 is that under the microscope you see these pinkish round blobs which are called Rosenthal fibers. And if you even go to a higher magnification at the electron microscope level, you also see these aggregates of proteins. And we now know that in these aggregates is a protein called GFAP. So one important thing is that to also know is that these aggregates are actually only in one type of cells. They are in the so-called astrocytes. And astrocytes are star-like cells and they are present throughout the brain, in the gray matter, but also in the white matter. And they are essential to keep the environment of the neurons here in blue. So the neurons are the cells that communicate with each other. But the astrocytes here in green, they are very, very important in making sure that the neurons can really do their job. So they will make sure that the iron concentration is right. They will make sure that these cells get a lot of nutrients from the bloodstream. And they really make sure that the communication between these cells is optimal. So in Alexander disease, there is a specific protein called GFAP accumulating in these astrocytes, especially also very close to blood vessels in these Rosenthal. That's why this cells is very important, and I'm very interested during my whole scientific life in this cell type, but also in this protein GFAP. So the disease we know now since 2001 is caused by mutations in one protein called GFAP, or one gene. And what kind of gene is that? Because if we want to try to develop cures, we need to know what the mechanism is why people get this disease. So GFAP is a part of the cytoskeleton, of the skeleton of a cell. So these are all cells. So that's like 20 micron thick, which is like a hair thick or even less. You can see these fibers within the cell in green, and that is actually the skeleton of a cell. And part of the skeleton is formed by this protein GFAP, and this is the protein which is mutated in Alexander disease, and this is the protein that will lead to a lot of aggregates in the cell. It's not clear exactly at the moment at which site of the protein is more important to get the disease, because as you can see here, so this is the full protein. And here are just every circle is a patient with a specific mutation at a specific site of the protein. These are the patients that get the disease at a very early age, and these are the patients that get the disease at later ages. But you can also see that the mutations are scattered all over the protein, which makes it difficult for researchers and biomedical scientists to understand why this is, and to also understand which part of the protein is the most important part to have this that lead to the disease. in all cases, what we do see, if we have a wild type protein, this is one cell. If you have the wild type protein in one cell, you get this very nice skeleton cell. I still hear myself back. So I think somebody has the microphone on.
Yeah, we do have an echo in the English channel.
Okay. I'll try to continue, but the echo is quite strong, right? At least in my end. I don't know whether other people also have the echo.
I'm checking with the translation.
Yeah. I think, Audrey, you will let me know when I can continue, right?
Yes. Maybe speak.
I can speak, yes. I don't hear an echo now.
So you can go ahead.
Okay, super. Thank you. So as I said, the mutations, so there's only one gene involved in this disease, but the mutations can cover the full length of the whole protein, and that makes it a bit more difficult to understand what's going on. What at least is happening is that if you have normal wild type, so normal GFAP, you find that this very nice skeleton in a cell. If you have one of these mutations, you see that the skeleton is not built and you get all kind of aggregates. And that's also what you can see under a microscope. So this is a human Alexander, this is an Alexander patient, and these green blobs are aggregates of this skeletal protein. So to be able to now I do hear the echo again. To be able, Audrey, is this on my side?
I hear your echo. Let me call.
Okay.
Actually, it seems that it's your connection.
My connection.
Yeah.
Okay. I'm really sorry about this, but I'll try to continue, and I think now it's fine again.
Yeah, it's fine again.
Okay. So to understand the biological mechanism is really essential if you're thinking about developing drugs to treat such a disease. And you can do that in several ways, and also Marjo van der Knaap and also Raoul STVS showed all kind of models for different diseases. So what we normally do is we make models in mice with GFAP mutations. We can look in brain tissue of patients that donated their brains after death, and we can make cell models. I will talk a bit more about cell models because that's work that I do in the lab, but I have one slide also on the rodent models. Very recently, there was a very nice paper from a group of ALBA Messing, and he is really the person that knows a lot about this disease. And they made a rat model for Alexander disease. And in this model, they saw a lot of pathology that was very similar to what they've seen in what is known in Alexander patients. So this is an example of that. So these are, if you look on the left side, this is the normal rat, wild type, and this is the rat with a mutation. And here you see these pinkish roundish blobs again, which are the aggregates of GFAP. What they also tested in this model was a new therapy, an antisense therapy directed against the messenger RNA of GFAP. And what they found is that if they treated these rodents, these rats, with this therapy, that there were no Rosenthal fibers. And that was really very promising. They also checked in these rodents whether all kind of general behavior stuff and also body weights was changing. And I will just show you one of these things. So this is, so here the rodents, the rats got the therapy at 3 weeks of age. And here you see over the weeks the weight of these rats, and these are the wild type rats that were either treated with a control drug or with the antisense oligonucleotide. So you see here it's not seems not to be very toxic. And this is the rats that have the mutation and that got the control drug. So these rats are really have a lower weight. But the rats that got the drug, so that are these one with the open squares, are exactly, you cannot distinguish them from the normal white type rats. So that's really, really very promising. And I know that there is a trial that has been started over the world, and also the Amsterdam Center of Marjo VAN DER KNAAP is involved in that by testing this new drug also in Alexander patients. It's called ION 373, or it's also called silganersen. So, but going back to these models, because this drug seems very promising, I think it would be really, really important also to develop other types of drugs and not only be reliant only on one drug. And for that, it would be really good to have also cell models which are a bit more closer to the patients. And there is a very interesting, I think, new method in biomedical sciences, and that is that you can make from every patient or every individual, you can make stem cells just by taking a little bit of skin. It's called induced pluripotent stem cells. And this makes it possible to have personalized medicine because you can check different drugs on cell models derived from individuals. For this new method, which was first published in 2012 by Yamanaka, he got in 2012, sorry, it was published in 2006, but 6 years later he already got the Nobel Prize. And that shows how important this new technology is for the biomedical field in the broad sense. So what you can do now is you can get stem cells from individuals, from every person. You can put them in a dish just from a bit of skin or from a bit of blood, and we can bring them back to the stem cell stage. And from these tissues, from these cells, you can make any type of tissue. But for Alexander disease, of course, it's very important that we can make brain cells from these iPSC cells, from these stem cells. And also another very nice breakthrough in science is that we can not only make single neurons, but we can also make like mini brains. We call them organoids. So you can make little brains or structures that look like brains from these stem cells. And that's what we started to study in our consortium that is called Alexander, to see whether we could find something, whether we could develop a nice model for Alexander disease. So how can you make brain organoids from skin cells from individuals, from patients or from controls? So you take a bit of skin, you make them into single cells, and then they call that reprogramming. You can put a few different pieces of DNA, and then you can reprogram these cells back to the stem cell state. Then there are very lengthy protocols, but they are very nice to follow. So you can mimic actually the development of one of these stem cells into first an embryoid body. And then by giving different types of growth factors to the cell culture medium, in the end you can make little balls like this that start to make brain cells, or it's called neuroectoderm. And we can keep them in culture. Here it says day 15 and day 180, but we can even keep them in culture for over 2 years, and they will keep growing. And this type of technology is really evolving, and it has been evolved over the last years. They look like this. So this dish is about 6 centimeters in diameter, and every little ball of cells here is a organoid, and these can be as large as green peas. And we culture them on these shaking platforms, which we call belly dancers, because they have to be in constant movement so that all the nutrients can reach also the inside of these organoids. We can visualize all the cell types in these organoids, and these are just, we have a method so that we can really see through one of these pea-size like organoids, and then we can start looking for all kind of markers for different cell types, and we can start looking, for instance, also for Alexander disease for aggregates in these cell models. So what we did is we started with skin cells of a few patients, and these skin cells were made into induced pluripotent stem cells so that we could make mini brains of them. But the important thing is that we, with another technology which is called CRISPR-Cas9, which I will not explain right now, but it is a technique so that you can repair mutations in DNA. We made a so-called isogenic control, actually derived from the same patients, but in this control, this one mutation has been repaired, meaning that the genetic background of the control and the Alexander patient's organoids is exactly the same, except for this one mutation causing the disease. So this is the ultimate control that you can have in this case, because every person has a different genetic background, and that can have an effect on the formation of the organoids. So we expected, of course, to find all kind of aggregates like here, so the Rosenthal fibers. So we thought we just culture them, and then we could check for the aggregates. One of the things we did is also look at the size of the organoids, and I told you in the beginning that Alexander patients have a bigger brain. And what you see here is 3 dishes with organoids of the control condition, and on the top you see 3 dishes with organoids of one specific patient, and you can see very clearly that in this case the organoids grow bigger, which mimics the patient condition in this case. What we've also seen, and that is when we look in the organoids at an earlier stage. The top is one Alexander patient, and here we just made very thin slices of the organoids and we put them underneath the microscope, and these are the controls. You see these very nice, we call them rosettes. Here all the 3 colors are here in one picture, but you can see that these rosettes are different in Alexander patients than in controls. The controls have a very nice thick neuroectoderm, thick rosettes. And the Alexander patients have a very thin rosettes. And this was one of the first indications that we thought there might be an effect on the differentiation of the cell types during these organoids. And this is something that we have seen now in several different ways to culture these cells. And almost every way we do it, we see an effect on differentiation. So what, for instance, what you see here, these are 2 markers for brain tissue. This is double cortin on the left side, and this is SOX9. So if this is expressed, then you know that you're looking at brain tissue. And you see that in the Alexander patients, so in the ones that were, so these are the repaired ones with CRISPR-Cas, and this is from the original patient line. You see that the number of double cortin positive cells, but also the number of SOX9 cells are also lower. This is another way to look at it, but again, the same message. So what we did here is we looked at single cell analysis, and we do that with a method called single cell RNA sequencing. We did that in several different control organoids, but also Alexander organoids. And what you can see then in a plot like this is that you see clusters of cell types in different colors that are from, in this case, the controls. And these are the clusters of cell types that we could find in the organoids from the Alexander. I think it's very clear that what you can see that, for instance, the astrocytes, so these star-shaped cells, were present in the controls, but were not present in the Alexander patients. And also specific subtypes of neurons we could only find in the controls and not in the Alexander patients. What what we also saw is that in this in vitro, in this culture dish, because the differentiation can really go fully wrong, because of course this is not directly comparable with a developing embryo, but this is a isolated system in a culture dish. But what we also saw is because when the differentiation goes wrong, it can go really wrong. We saw more muscle cells in brain tissue, and we even saw pancreas cells. The main message also again for this is that during early development there is either a differentiation delay, or the brain is not developed in the way it should be. And that might lead in the end also to the white matter problems, but that's something that we still not fully understand. So we have a huge phenotype in organoids from different patients. And in all of these patients, we see that there is a problem with differentiation into the full mature brain cells. And this can either be a total lineage commitment problem or a delayed differentiation. In the older organoids, if you can grow them very large, we see that they are larger than control organoids, and we also do see Rosenthal fibers. But I have to say that it's much more clear in the rodent models. So my message is also that the organoids and the rodents model the disease, but really in a different way. So what I think the human models can be used for is to screen novel drugs that can reverse or prevent the phenotype that I showed you. And this could be in the end also personalized medicine, what researchers also have done, for instance, for cystic fibrosis, to make mini guts that we can bring for drugs. But then, of course, also important to test the rodent models, because then you can really screen for much more, like behavior or gait, as Marjo van der Knaap just showed, and not only the clump of cells in a dish. So I think both models are important in the end to learn more about the disease, but also to work towards a cure. So the work that I showed you was part of a European Joint Program of Rare Diseases, and ELA is a partner in this project together with the Dutch White Matter Disorder Organization. And this is a project with a group from Sweden, Milos Pekny from Prague, Mikael Kubista, Itamar Harel from Israel, Henrik Aleni is also from Sweden, and Dolores Perez Sala from Spain. And we are now writing up 2 manuscripts that we will submit for publication in the next 2 weeks. So these are the people that were part of this project. A lot of the organoid work was done by my PhD student Werner Dijkstra, who is almost ready with his thesis and will defend hopefully before the end of the year. And I also would like to say that in this year we will start a new program fully funded by ELA, and I'm really happy that ELA is funding this project. And this is a project that I do together with Marjo van der Knaap from the University of Victoria. And we will now look into the organoids, but at the electron microscope level, to see whether we can find, for instance, also Rosenthal fibers, but also other pathology. And what you can see here, this is really nanometer scale, so very, very thin. That's why we also called the project Alexander disease at the nanoscale in patient-derived organoids. But we already find, for instance, changes in the mitochondria, which are the energy factories of the cell. But I hope that I can show you more in next year or maybe in 2 years. So thank you very much for your attention. And I'm sorry about the problems with the sound.
Yeah, very nice talk, Elly, as well. Although they have problems, but it was very good. So, okay, finally, we are doing the last talk of today. Is going to be done by Annette BLEY from Germany. And she will talk about another interesting disease, is Canavan disease, basics and updates. Thank you, Annette.
Yes, thank you. Can you hear me?
Yes, yes.
Good. So, yes, thank you. It's my pleasure. Thanks, Ela, for the invitation to talk about Canavan. And yeah, let's start. Hang on, my doesn't really. Just 1 second. Can't move forward. Just a second. I stop it for a second.
With arrows, Annette, you can.
Yes, I tried. It didn't work. So it works. Now.
Okay.
Now it works. Okay, sorry, don't know. Okay, these are my disclosures. I'm PI for the ALBA Therapeutics natural history study for the gene therapy trial that I will mention a little later, and PI for research cooperation that is investigating for effects of NAA. Okay. So Canavan disease, as all of the leukodystrophies you just heard about, it's a rare and fatal leukodystrophy, and I just move the videos here, and yeah, it causes progressive damage to the glia, to nerve cells in the brain, and it's leading to progressive loss of neurological functions, helplessness, and premature death. There are different names for Canavan disease. I'm sorry, I just tried to move the video, the picture here of the. Now that's better. There are different names used for Canavan disease. Not very common, but sometimes still used is Canavan van Bogaert-Bertrand disease. And describing the histology, it's the spongy degeneration of the central nervous system, or describing the enzyme that is losing the function. It's the aspartate deficiency. As all leukodystrophies, it's inherited, and this one, Canavan, is autosomal recessively inherited. The ASPA gene is located on the chromosome 17, and as said, is leading to the dysfunction of the enzyme aspartate. Here is a simplified model, or just to enable explanation. What do we know, or what is important to understand the pathomechanism that is not fully understood yet. And we know that NAA is produced in neurons. NAT8L is involved in production of NAA, and we know that NAA is then transported and taken up by astrocytes and oligodendrocytes. There was a lot research going on about specific mechanisms. It's not fully understood yet, and but we know it's taken up, and we know it's degraded by the enzyme aspartate, for example, in the oligodendrocyte. And if this happens, then it's degraded to acetate and aspartate, and this is the usual way. If aspartate is deficient and not working properly, NAA is not degraded and is elevated, and we have less acetate and aspartate. So that's what we know for sure. And then there were a lot of hypotheses and theories how exactly this leads to the degeneration of the brain. We know, and here's a little very small picture on the right lower side, we know if that happens, then the brain has a spongious appearance. It's swelling, and there's a lot of fluid between the regular brain tissue, and it has a spongious appearance. So we do not really know how that works. There were different theories. Oops, And one theory that the acetate that's available by splitting the NAA, that this is needed for lipid layers, it wasn't proved, and there were mouse models proving that you don't need NAA to be split, and you don't need acetate by NAA, because there were double knockout mice who did not produce NAA and did not have aspartoacylase function, but still showed myelination. So it's still not 100% or not really clear how the degradation or the degeneration of the brain happens, probably by osmotic or eventually by osmotic pathways, but it's something this needs to be elucidated further. So if we have a patient and we have the suspicion that there might be a Canavan disease causing the symptoms of the patient, there are different ways or possibilities to prove that. Luckily, there is we can use the high NIA levels as a biomarker. So and luckily, it's not only in the brain high, it's also very high in the urine. And it's quite a cheap or simple analysis. If you order in a metabolic lab organic acids and they are elevated, it's pathognomonic for Canavan disease. So it's relatively easy to get to the diagnosis. There are other diagnostic tools that we use. Molecular genetic, of course, is an important one. In the ASPA gene, finding the two pathogenic variants. And I already talked briefly about histology. MRI shows specific or not, shows special or shows patterns that lead to the suspicion of Canavan disease, with pronounced affection of subcortical white matter, the thalamus, basal ganglia, and the cerebellum as well being involved. And if we use the magnetic resonance spectroscopy, we see the elevation of NAA also here, which is proving the diagnosis. The fibroblasts that I mentioned here, there are possibilities to show the reduced enzyme activity of the aspartoacylase, but this is nothing we really use in daily diagnostic life. Here I just picked out very few, in my opinion, important publications. I just wanted to highlight a few over the last decades. The first, because it was the name-giving one in 1931 by Myrtle Canavan, the first description of the sponge's appearance. Then later in the 80s, detection of the high NAA being correlated with degeneration of the brain. Then then later the aspartoacylase deficiency in the 90s. Then the detection of the ASPA gene. Little later, knockout mice and different working groups in Australia, New Zealand, US, doing research on intracerebral or other gene therapeutical approaches. And then the first trials with patients with gene therapy, and later other mice publications about gene therapeutical approaches, not only IV or intracerebral, but also as antisense oligonucleotides in mice at least. And it's a very exciting spectrum that is looked for, or that's published in the last decade. So now I would like to go into the cause and would like to describe the cause of the disease. So it's known, as shown since quite a while. This here is a graph from 1996, and we adapted it a little bit. This is representing the typical and, let's say, severe cause of Canavan disease. And we see that most of the findings already happen in the first year of life. So it's a disease where usually children are affected very early, especially the typical form of Canavan disease. So even if almost or all patients appear normal at birth, the onset is very early, within the first months of life, and they show signs and symptoms as hypotonia of the trunk. They have spasticities and abnormal eye movements. Then the head is growing too fast. They develop macrocephaly. They have visual fixation problems, and the seizures occur and rise in the number. And it's a severe disease of very early childhood. And 3 years ago, we published a natural history study about 23 patients and patients from literature. And last year, there was an updated gene review about Canavan disease that gives a little more information. And from these publications, I just would like to cite a few. Coming back to the onset of the disease, the first symptom, as I said, is occurring usually very early. So sometimes in the first month of life, sometimes in the first half year. And usually the patients do not only show one symptoms, they usually have 2 or up to 12 symptoms at onset. So here's a list of the symptoms the patients present. Developmental delay is very common, so they just do not gain the milestones we would expect them to gain, like reactive smiling, like visual fixation. Many of them show the muscle tone abnormalities, the floppiness of the trunk, and going with that, the lack of head control, abnormal eye movements I already mentioned, the macrocephaly progressively developing, some irritability, and so on and so on. Feeding problems are important as well. And as an update, I would like to mention that in the publication from 2021, we analyzed a cohort with mainly severely affected patients. There were 3 not as severe as the most of this cohort, but since then we're following more and more patients, and we have 8 patients that we follow since some time, and they are atypically mild, even a lot milder than the ones that we described in the paper in 2021. And even if they are a lot milder, they still had 7 out of 8 had their first symptoms within the first year of life, even if these symptoms are not as pronounced or severe as in the typically affected patient. The diagnosis is usually made quite quickly, by genetics or biochemical proofs. And just one quick or short update. In our cohort of 56 patients, we had 18% of the patients who had clinically, from the MRI and from the NAA elevation in urine or spectroscopy, they only had one pathogenic variant. And we started a cooperation with the human genetics department in Mainz, who were already involved getting deeper into intronic variants, and we have a promising candidate right now. And we hope to solve that and help these families. It's important because if you only have one pathogenic variant known, it's a lot more difficult for the families, for further family plannings, for potential participation in trials, in clinical in gene therapy trials. So it's quite important to know those candidates. This is a figure showing the head circumference over time in patients. This figure was published in 21, and it shows quite nicely that in the published cohort, most of them in the first year, they cross the percentiles. The gray area is the gray area, and the curves with the gray area are the healthy, normal developing children, and the black lines above that is the Canavan cohort, and they all cross percentiles within the first year, some until the 18th month of age, and they yes, all show a macrocephaly after some time at least. The mentioned milder cases that I just mentioned before usually have normal head circumferences, or for some time a little elevation, a little up, yeah, some mildly elevated head circumference, but not as pronounced as the typical Canavan patient. So that's the 18 months, where usually all typical Canavan cases have macrocephaly. This is a Kaplan-Meier figure showing survival probability. I just would like to highlight that in the older literature, Canavan disease is thought to be or lead to premature death within the first few years of life. So we were, I don't want to say astonished, but we showed here that at least in our cohort, 73% survive until the age of 10 years. And these patients, as I mentioned before, this cohort does not include the 8 patients with the, let's say, atypical mild cause of the disease. So this might be a lot longer, and it's not really clear yet what life expectancy in mild cases is. In 2021, we published, in cooperation with Florian Eichler in Boston, this paper, and we also published here the score, the CDRS, the Canavan severity score, and there are 11 items that we found in many Canavan patients, and that we use to describe the severity. If a patient is not showing any of these symptoms or signs, then the patient has 0 points. If the patient has severe or pronounced or constant symptoms or problems, then it's scored with 2. Intermittently or mildly, symptoms are scored with 1. So it's we use that score since a few years now, and need to reevaluate it, of course, but it seems to give a good picture of the severity to our impression. Okay, this is just a few figures. Beside the symptoms that we observe and that we follow, we have some questionnaire for medical aids and the situation of care for our patients. And this is just 4 out of a list of 20 questions or items that we ask and try to note or to collect over time, to get an impression about the need of medical aids, and showing just here as an example, physiotherapy. It's even in the first 2 years, over 80% receiving physiotherapy, and then after the age of 3, 100% of our patients at least receive physical therapy. Okay, here's a little comparison between the typical form and the atypical form. Just a few highlights. It's not showing the whole comparison, but as mentioned, the typical Canavan patient shows severe neurodevelopmental impairment early in life, in the first months, at least year. The atypical patient also shows early neurodevelopmental abnormalities, but it's more subtle, it's more mild. It's not the case that the atypical patient does not reach the milestones like no reactive smiling, no visual tracking, no grasping, no sitting, even no supported sitting. The atypical patient, Canavan patient, learns all that, but sometimes a little later. Sometimes there are little muscle tone abnormalities. They have a little truncal hypotonia. It takes longer. Turning from side to side turns longer. Sitting without support takes longer than it usually would be expected in a healthy child. What is the striking difference is all the patients who we describe as atypical, they learn to walk, even if part of them or some of them use a walker, but they walk. And in the same, and they talk, even if it's not comparable. By most of them are not talking like a healthy person, but words, they are all able to talk in words, and some talk in sentences. And this is some striking difference if we compare it with the typical Canavan patient. The head circumference I already mentioned, which is usually normal in the atypical Canavan patient, and it's always enlarged in the typical Canavan patient. They all are able, the atypical, mildly affected Canavan patients, they're all able to see. And they show the regression that we see quite early in the typical patients, a little, or not a little, we see it later, but we only follow a few older patients, so it's really difficult to say when we would expect regression in the development or regression for these patients. But we think that the variability is a lot higher. We see the variability is a lot higher than in the typical Canavan patient, where it's more clear what we expect. This is just two pictures. On the left-hand side, we see a 1-year-old Canavan patient with a typical Canavan disease. Already the shape of the skull and the brain is abnormal compared with the 1-year-old Canavan patient who has a mild cause of the disease, and the grade or the degree of demyelination or hypomyelination or not abnormal myelination is a lot worse in the typically affected Canavan patient. There are abnormalities in the thalamus and the basal ganglia as well, as mentioned earlier. And it's interesting that the pattern is a little different. If we look at the mildly affected Canavan patients on the right side, there is as well abnormal myelination, but the nucleus caudatus, let's see if I have a there, the nucleus caudatus has an abnormal signal, which is not as abnormal in the severely affected child, and the putamen shows abnormal signal, which is not shown in the severely affected child. So the pattern is a little different, which is at least by us not understood, and needs to, we would be interested how we could explain that. So what is the need? What do we need? We need a deeper understanding of the pathomechanism and a better knowledge of the cause of the disease. We need more diagnostic tools to allow a timely treatment as newborn screening. We need the development of effective and medically acceptable treatments for younger but also for older patients. And a few aspects for that. We are involved in a research cooperation with, it's sponsored by the Federal Ministry of Education and Research in Germany, and the Technical University in Braunschweig and the Helmholtz Institute in Munich work with us together. And the colleagues come from, they started with some cancer cell analysis, and what we do here is we look for pathomechanisms in cell models, and together with the analysis of patient fibroblasts and other parameters from patients, clinical and laboratory parameters. There is the colleague from Munich is working on computational models, and we try to get deeper insight into the pathophysiology of Canavan disease. And we in Hamburg had some additional aims that we wanted to achieve. Just one thing that just went well or just worked out is the development of Canavan disease newborn screening. Even if there is no approved treatment yet, there are studies. We'll mention it in a minute. There are studies ongoing, and we already, or my colleague Simona Molko worked on a method, and it allows a very good differentiation of affected and healthy human babies, newborns, and it's just under review, and we hope to start at one point with pilot screenings there. And we have other projects ongoing. Characterization of peripheral immune cells in CD patients is one of them, but I don't want to go into too much detail now. So now for most patients, probably the most interesting part. There are two ongoing gene therapy trials. One is done by Myrtle Gene Therapeutics, and unfortunately, I do not have too much details about that from the clinicaltrials.gov website. I have some information. Here's a very short extract. Patients from until the age of 5 years are included. If I see it right, it's active, but it's not currently recruiting further patients. And it's a gene therapy directly applicated into the brain with a AAV vector that's specific for oligodendrocytes. So that's just a short description of that treatment or trial. And ALBA Therapeutics, it's another company doing a phase 1/2 open label study as well. They use a AAV9 vector intravenously, and they still recruit patients. We in Hamburg collect data for the natural history comparison group. And in the natural history study, every patient, even deceased patients, where we just do retrospective data collection, every Canavan patient can participate. Prospectively, there's a whole bunch of assessments that's done to allow a good comparison. The key inclusion criteria for the gene therapy trial is diagnosis of Canavan, of course, stable health situation, and the age below 30 months. And ASPA provided some information that I am allowed to present. So these data were already published, and about 8 participants, the first 8 participants that received the gene therapy, and they tolerated the IV infusions well, and there was a sustained NAA reduction in CSF and urine, and brain NAA. There was in MRI, there was seen some improvement of myelination, especially infra in the cerebellum, and very early positive trends in motor outcome data. Okay, to sum up, as mentioned in the other talks, for Canavan as well, there is a high need of better understanding of the pathophysiology. And as mentioned in other talks as well, there's already, even if we do not understand everything fully, there are ongoing treatment trials, which is important. And the development of early diagnostic tools is important. my colleagues from the newborn screening lab did some work there, but still there's a lot to do. Pilot studies are needed, and yeah, the aim is to treat, if possible, all affected patients. Okay, thank you very much. Especially thanks to our patients and their families who really support the work, and then to all the co-workers, supporters, cooperating partners, and of course to my team who's very busy and supporting. Thanks.
I found it. Our next speaker is Soumeya BEKRI from France, who's going to speak a little bit about newborn screening for MLD, and in the context of some of the new approvals for MLD with Medley, a very encouraging and promising thing. And she comes to us from Rouen University Hospital, and I look forward to her talk. Thank you.
Thank you very much, Adeline, for this introduction. I would like to thank the ELA Association for their invitation and to giving me the opportunity to share with you this talk entitled Newborn Screening for MLD, a Global Perspective. This is my disclosures. We know that metachromatic leukodystrophy is a rare lysosomal disease characterized by the accumulation of sulfatide due to the disruption of their catabolism. And this disease is characterized by heavy central nervous system and peripheral nervous system alteration. And we know also that newborn screening has a crucial benefit effect if we are able to detect such severe pathology in a presymptomatic stage. We will be able to introduce efficient therapy when they are available, and then to reverse the prognosis and to improve the prognosis when the treatment is initiated in a very early manner. For metachromatic leukodystrophy, it's the case. We can really reverse this prognosis if we do the diagnosis at these stages. That's why we have several initiatives at the international level for newborn screening, and there are more than 250,000 babies that have been screened for MLD, and 14 MLD and newborn screening studies are today ongoing, either retrospective studies for validation method purposes or prospective study. And we have two different strategies: biochemical investigation as first-line investigation or genomic as first-line investigation. Then we can perform the control with the other investigations. Regarding the retrospective study, they are based on biochemical approach as first-line investigation, and we are aware of 3 of them in US, UK, and in France. When it comes to the prospective study, we have two strategies are deployed: biochemical strategy with 7 or 8 study that are ongoing right now in Germany, Austria, Saudi Arabia, Italy, US, and Rouen in France in my lab. And for other additional pilot study are conducted using genomic as first line. These both approach have their drawbacks, and biochemical investigation may end up with false positive cases due to the enzyme activity pseudo deficiency that we have for some enzymes, and also we can have heterozygous stages that may lower the enzyme activity and increase a little bit the metabolite, and we recall the baby even if there is no real, it's false positive, then this is the limitation of the biochemical approach alone. For the genomic approach, also, conversely, we have this this approach can lead to the identification of variants of unknown significance, complicating the interpretation and potentially resulting in false negative findings. Then I think that I will discuss this at the end, but I think that we should think about combining these two approaches to solve a part of this problem. I will now describe the LISO-NEO project, the pilot study dedicated to the newborn screening for lysosomal disease in Normandy region. This project has been done in a close collaboration with the Réseau de Périnatalité de Normandie. It's all the 23 maternity hospitals of Normandy that have been involved in this project, and the promoter is Rouen University Hospital. We got the ethical approval on May 2020, but we succeeded to start in March 2021 due to the COVID pandemic, and we are aiming to include 100,000 babies in this study. This study involves also the regional center for newborn screening in Normandy. It's based in Caen, another city in Normandy, but we set up this project together. At the first part, when we started on March 2021, the LISO-NEO project was dealing with 11 lysosomal disease. But meanwhile, 2 other pathologies have been added, since we had at this time the synthetic substrate that we can use for the assessment became available. Then we added lysosomal acid lipase deficiency and metachromatic leukodystrophy to our panel. And this extension has been done on March 22. And the idea is to catch up with the primary study, and the time period was 2 years, with the inclusion rate will be 66,000 babies. To have this project done, we gathered several specialists from different hospitals, biologists, pediatricians, geneticists, so on, in all the university and the big hospital in our region. And thanks to a strong public-private partnership, we were able to gather the financial support to set up this project. And the primary objective of this project is to evaluate the feasibility of systematic neonatal screening for MPS 1 and Pompe disease, since this mucopolysaccharide 1 and Pompe disease has been included in several newborn screening worldwide. And we used for this multiplex analysis using lysosomal enzyme activity on DBS, on the dried blood cells spots. And the idea here is to screen a cohort of 100,000 newborn in Normandy region. But since we are using multiplex analysis, we can assess on the same sample other lysosomal pathology. That's why we built another ancillary study to screen for 11 other pathologies: Krabbe disease, Niemann-Pick AB disease, several mucopolysaccharidosis, neuronal lipofuscinosis type 2, and we added lysosomal acid lipase deficiency and metachromatic leukodystrophy. Regarding the inclusion, there was no limitation. All the newborn born in a maternity hospital in Normandy could be included if the parents agreed and if they signed the consent form. There is no exclusion criteria. And we decided to deploy a tiered investigation. The first investigation will be based on enzyme or metabolites. In the case of leukodystrophy, metachromatic leukodystrophy, we decide to start by the metabolite, the sulfatide. And if this first tier is positive, we add other investigation. In the case of MLD, we will assess the ARSA activity. And for this project, we call in the baby to control the abnormal results and to perform genotyping for ARSA gene and other gene. The second step. To do this, we use two platforms, a mass spec based platform from REVIT, and this is for the biochemical investigation, and for the NGS, for the genetic investigation, we use a next generation sequencing on Illumina platform, and we use a panel, lysogene panel, an in-house panel, including 52 lysosomal diseases genes. Then the algorithm used for the MLD was as following. For the first DBS and the newborn screening DBS, if we have high sulfatide concentration, we will assess again on the same DBS, the sulfatide, and then perform the ARSA activity assessment. And if this activity is low, we consider that this DBS is positive, and we will do a multidisciplinary commission at national level to discuss this case. And then we call in the baby to have samples for control, and we will perform again the sulfatide and ARSA activity. And if it's still positive, we will do the genotyping. And for the patient management, we will also have this multidisciplinary discussion at a national level. Then for the Lysoneo primary study that started on March 2021, we started on March, and if we can, as you can see here, at the last January, we reached more than 80,000 baby included in this study. And we are lucky because the rate of refusal is very low, less than 6%. And regarding the extension study, since we started 1 year later on March 2022, we reached right now 56,000 baby included. The Lysoneo study enabled us to learn lessons, and my conclusion is the fact that we are using biochemical investigation as first-line approach. This strategy may lead to false positive, and we have to recall babies even if they are not actually affected, but they are still called to perform further investigation. And this algorithm led to an increased stress for the parents and an unnecessary mobilization of healthcare professionals. That's why for the following step, we are aiming to adopt another strategy and to perform an integrated approach using biochemical and genetic investigation on the initial DBS, on the first DBS, and to call in the baby only if all these integrated results are point toward a positive result, a positive suspicion. Then I think that using this strategy, we will lower the unnecessary call, and we will focus on the true positive cases. And when we recall the baby, we will do all the control investigation at the biochemical and genetic level. And for the positive, we also go for the multidisciplinary discussion at the national level to have the right decision regarding the management of the patient. This management is done within a reference center in Normandy region, but also on collaboration with other reference center in Paris, essentially, and in other competence center within Normandy. And this pilot study, altogether with other pilot study, led us to precise the algorithm for MLD. We are proposing to have as a first-tier analysis the assessment of sulfatide, for the second-tier analysis the ARSA activity, and for the third-tier analysis the ARSA genotyping. And this integrated approach lead to propose a very efficient strategy for MLD to integrate national newborn screening. Furthermore, regarding the sulfatide, we have used the sulfatide, species of sulfatide, which is C60 sulfatide, and thanks to this collaborative international work, we end up that the use of another species, the C16-1-OH sulfatide, leads to a higher precision for this approach and for this diagnosis and improve the global strategy. This work has been published recently, last March, and at the same time, another group that take part of this, our international work too, but this other group gave us some recommendation from their preclinical study to identify late and infantile cases for treatment. Regarding the clinical management, an European consensus has been published recently towards the newborn screening of MLD. Then the ultimate goal is to expand at a global level the screening for MLD, leveraging the insights gained from pilot studies and scaling up the national program to cover this disease requires collaboration with national authorities, political decision makers, health professionals, and patient associations to ensure the synergy and the effective implementation. We are really willing to have this disease that are treatable to be part of the newborn screening at a national level. Now, I would like to thank all the participants of the Lysoneo project, the newborns and their parents, the medical staff, and the reference center for lysosomal disease in France, and all our partners. And I am happy to take any question if you like. Thank you.
I think we're going to keep questions for the end, if I understand specifically. Dr. Bekri, thank you so much for your very nice talk. If it's okay, and if Caroline SEVIN is ready. Good morning, Caroline. We'll have Caroline presenting. She's coming to us from Bicêtre Hospital, also in France, and she's going to discuss therapeutic options for metachromatic leukodystrophy and Krabbe disease, and sort of where we stand in the progression of that as we see therapies evolve. Thank you, Dr. Bekri.
Thank you.
Thank you, Adeline, for the introduction. I will share my screen. Is it okay? Can you hear me and can you see the...
We can hear and see you, yes.
Perfect. Okay. So, good afternoon or good morning, everybody, or good evening, I don't know. I am very happy to be here, and thanks to Ella for the invitation and for giving me the opportunity to make an overview of therapeutic option for two leukodystrophies, metachromatic leukodystrophy and Krabbe disease. These are my disclosures. So both metachromatic leukodystrophy and Krabbe disease share some characteristics. First, both are lysosomal storage disorders, mainly restricted to the nervous system. And in the early onset form of this disease, there is sorry, I just want to take this. Okay. In the early onset forms of this disease, there is, after normal development and stagnation, a very, very rapid deterioration that is more or less severe in late onset forms. More often, late onset forms are more slowly progressing. Both leukodystrophy, of course, have a presents are demyelination, neuronal degeneration, and also, and I will talk about that maybe later, neuroinflammation, which is an important part of the pathophysiology of this disease. There is currently no curative treatment for the early onset forms of metachromatic leukodystrophy and Krabbe disease once symptoms are already present. That is unfortunately today the most frequent situation. And in later onset forms, juvenile or adult forms, hematopoietic stem cell transplantation can modify the clinical course of the disease only if performed pre-symptomatically or in patients with very early symptoms of the disease, and once again only in late onset forms. I will speak, of course, during this talk about ex vivo gene therapy for metachromatic leukodystrophy, which is a LIMBLD that has really changed the outcome of children with asymptomatic early onset metachromatic leukodystrophy. And in both these clinical trials are currently running. So before speaking about the disease, some generalities. First, we must consider that there are a lot of challenges to treat MLD and Krabbe disease, like other neurodegenerative disease. Any treatment that we will choose must of course enter into the CNS, the central nervous system, and avoid either by direct administration, either by strategy avoiding the blood-brain barrier, because of the blood-brain barrier doesn't allow a product to go into the brain. The treatment should and must target the right cells at the right time and at the right place, and this is not so easy, and for that we should know exactly the pathophysiology of the disease. The treatment should be administered as soon as possible, and ideally, the best option, of course, is to treat before the apparition of the occurrence of the symptoms. The treatment should lead to a stable expression. Of course, it shouldn't be toxic. That's the main point, of course, when we develop a new treatment. In MLD and Krabbe disease, we mainly target the central nervous system and the peripheral nervous system. So in other disease, we should also target other tissues, but it's not the case in MLD and Krabbe disease. And of course, we should know the pathophysiology of the disease, because as you see in the graph on the upper left graph, the usual presentation of this disease is that after a normal development, the children have a kind of stagnation of their motor acquisition, and then suddenly there is a rapid degradation. So we have the pre-symptomatic, the early symptomatic stage when there is this stagnation, and then the symptomatic stage. And of course, any treatment would certainly have a better effect if we treat pre-symptomatically. It could have an effect if we treat in this early symptomatic phase, but we can understand that unfortunately, when we are there in this phase of rapid degradation and also at the late onset, at the late stage of the disease, I mean, when the patient have already lost motor and cognitive function, it will be very, very difficult to treat at this moment. So the pathophysiology and the natural history of the disease is, of course, very important to know. And in terms of pathophysiology, these two diseases, as I said, are lysosomal storage disorders. So the main feature is accumulation of a non-degraded material. It's a storage. That's the reason why we named this disease lysosomal storage disorders. There is a storage in the lysosome of macromolecules that cannot be degraded. And this accumulation, this storage, led to secondary mechanism, and mainly, I would say, neuroinflammation, oxidative stress, problem with the energy metabolism, and that lead to the symptoms. In metachromatic leukodystrophy, the substrate that accumulates is sulfatides, and sulfatides are mainly present in the oligodendrocytes, and that's the reason why oligodendrocytes are the main targeted cell in terms of pathology, and there is a death of the oligodendrocytes and then of the neurons, of course, neuronal degeneration. But there is also this impact on the inflammation on astrocytes and microglia cells, which are the cells that trigger neuroinflammation. And that's the reason why in MLD there is also a neuroinflammation. In Krabbe disease, the substrate that accumulates is psychosin, and this substrate is very toxic for oligodendrocyte and is also very pro-inflammatory, and the storage of psychosin leads to neuroinflammation. So the main symptoms, leukodystrophy, neuronal degeneration, and neuroinflammation led to the clinical signs. And what can we do when we want to treat these diseases? It's the same for any disease, but for metachromatic leukodystrophy and Krabbe disease, because we are speaking about this disease. First, we can try to correct the gene, either by in vivo gene therapy. It means that we bring the gene into the brain, for example, either using correction of the protein deficit, and that's the rationale for intrathecal enzyme replacement that we will speak about in metachromatic leukodystrophy. Either, and it is also of importance, we may act on secondary defects due to the pathophysiology of the disease. And as I said, neuroinflammation may be a target, oxidative stress, endoplasmic reticulum stress, problem with energy. And for these secondary defects, we may use small molecules that are not specific for this disease, but that are known to have an effect on this secondary mechanism. And what is interesting is hematopoietic stem cell transplant and ex vivo gene therapy, because in this context, we replace the hematopoietic stem cells of the patients, or we correct the hematopoietic stem cells of the patient. It means that first we will bring into the brain corrected cells or normal cells, and these cells that will go into the brain are mainly immune cells and macrophages, and we correct the deficiency in these macrophages. So we change also, we will see that later, the immune system. It means that we both act on the gene or the protein defect, but also on probably neuroinflammation. To go better into details, for in allo hematopoietic stem cell transplant, it's bone marrow transplantation. After we have given the donor cells to the child, some cells, some immune cells, are able to migrate into the central nervous system and replace the affected or deficient central nervous system immune cells named microglia or macrophages. So we have the correction of these cells, which may have an effect on neuroinflammation. We have also the kind of reset of the peripheral immune system, and we know that maybe also the peripheral immune system may have some impact on the disease. Of course, we have to do a myeloablation just to empty the bone marrow so that she can be able to accept the new cells, and we have to do an immunosuppression. One important thing in this treatment is that there is a delay in action from 9 to 12 months, because the turnover, the replacement of the affected microglia cells takes some time. When we talk about, and because we will talk about that, so I just give a small information of what we name ex vivo gene therapies. It is in fact an autotransplantation of genetically modified hematopoietic stem cell. It means that you take the hematopoietic stem cells of the boy, of the girl, of the patient, you correct these cells with a therapeutic vector. It's an ex vivo correction. It's made in the lab. And then you re-administrate intravenously the corrected cells to the patient. And after, it's the same mechanism that for allo transplant. It means that some of the cells will go into the brain and differentiate into a macrophage or microglia. The advantage for this technique in comparison with classic allogenic stem cell transplant is that, of course, you don't have to search for a donor. There is also a myeloablation, like in allo transplant. You don't have to do an immunosuppression after the transplant. And as we will see, we expect to have at least the same effect or better effects. And we should mention here that for both procedures, the rationale to correct the enzyme activity into the brain is that it is based on the fact that the corrected cell or the normal cells from the donor are able to secrete the recombinant enzyme that can be endocytosed by other cells. It means that we correct only, of course, the immune cells, but they are able to secrete the protein, and the protein can be endocytosed by neurons or oligodendrocytes or other cells. And of course, it is very important in this procedure. Just a word on the difference between ex vivo and in vivo gene therapy. Ex vivo gene therapy, I have already explained that. And in comparison with in vivo gene therapy, where the most used vectors are AAV vectors, adeno-associated vectors, that you can put directly into different tissues, the brain or the spinal cord or the liver or the heart or whatever. And in the context of brain disease, usually these vectors mainly go into the neurons. But as I said, in metachromatic leukodystrophy Krabbe disease, the enzyme can be secreted and endocytosed. You can use with this approach different routes of administration, of course, directly into the brain, into intracerebral ventricular injection, also into the ventricles, into the CSF, the cerebral spinal fluid. And also you can now, because we have new vectors that are able to cross the blood-brain barrier, you can administrate it vector intravenously. That is, of course, easier. The difference between hematopoietic stem cell or ex vivo gene therapy is that with this method, you have a very rapid effect. In a few weeks, 2-3 weeks, there is a maximal expression of the recombinant protein. So now we will just talk about these two diseases. Metachromatic leukodystrophy is a lysosomal disease. It's caused by the aryl sulfatase A enzyme. It's one of the most frequent leukodystrophy in children after adrenoleukodystrophy. There is an accumulation of sulfatase that leads to demyelination, neuronal degeneration, and neuroinflammation. And the most frequent form of the disease is the late infantile form, at least in France, because in some other countries there are more late onset forms. But in France, the most frequent is a late infantile form with onset before 30 months, and with this classical evolution after a phase of normal progression, and then this phase of stagnation. There is a rapid degradation, first motor deterioration with loss of walk, loss of sitting position, and loss of all motor function, leading to a vegetative state. And a few weeks, I would say, that after the motor symptoms, there is also progressive cognitive regression and a very, very rapid progression. For the later onset forms that occur after 6 years, the progression is slower and less homogeneous. It means that there are some difference including in the same family in terms of progression. And most often, but not always, cognitive deterioration occurs before motor deterioration. So early onset forms occur before 7 years, late infantile and early juvenile, and late onset forms occurs after 7 years. What can we propose today as treatment for metachromatic leukodystrophy? First, hematopoietic stem cell transplant is used for years in metachromatic leukodystrophy, and we know now that this treatment modifies the natural course of the disease, particularly in late onset forms, late juvenile and adult patient, but only if performed pre-symptomatically or in patient with very early symptomatic clinical status, meaning globally no or very mild motor signs and a normal cognitive evaluation. But whenever, even if we treat the patient sufficiently early, we know also that hematopoietic stem cell transplant does not correct completely the disease, and that's some symptoms of the disease, even if they are very slowly progressing, are present, and particularly because the treatment has no sufficient effect on cerebellar symptoms, on the gray nuclei involvement, and also on peripheral nerves. There may be also a cognitive degradation. However, clearly, if patients are treated pre-symptomatically or early symptomatically, they have a different disease and very slowly progressive disease. This treatment has no effect in symptomatic early onset patients, late infantile and early juvenile patients. If they are pre-symptomatic, the treatment has no effect and may even accelerate the disease. That's the reason why we do not perform this treatment in these early onset patients. Now, ex vivo gene therapy, you know probably this treatment because now is available in most European countries, either because there is a market authorization or because they can be given as compassionate use. The story of this treatment is incredible because really, in comparison with hematopoietic stem cell transplant, I show you the slide with the comparison between the two methods, and we could not anticipate such a difference in terms of effect. There was 2 clinical trials that were performed in Milano by Francesca Fumagalli and Valeria Calbi. and also before that, Alessandra Biffi. Around 40 patients were treated, either pre-symptomatic patients with late infantile or early juvenile MLD, or early symptomatic patients with early juvenile MLD. The first thing, of course, was that was shown that there is a favorable risk-benefit profile with no important side effects. And now we have a follow-up of more than 10 years. So it's an important duration in terms of toxicity. This treatment allows a restoration of the ARSA enzyme demonstrated by a high level of ARSA activity in the blood, but also in the cerebrospinal fluid. And most important, of course, a significant improvement in survival without severe motor impairment in pre-symptomatic patients. Almost all the pre-symptomatic patients retained the ability to walk, and it was the results were less impressive in early juvenile MLD patients when they are already symptomatic at the beginning of their symptoms. And in both cases, there was a preservation of cognitive function compared to the natural history. For this reason, the product, which name is Limbeldi, had obtained a European marketing authorization in December 2020, and more recently in US. And for the late juvenile patients, there is still a clinical trial running in Milano. And now we can obtain this treatment in some European countries, as I said, and in France we have already, for example, treated 4 patients, in addition to 2 patients who were treated in the clinical trials. Just these 2 slides to show the impressive results. On this slide, you have represented the percentage of patients who are able to walk after Limbeldi without support compared to the natural history. In dark gray, you have the patient who received the treatment, and you see that almost 24 up to 25 patients are still able to walk years after the treatment, whereas in the natural history, almost all patients lose this ability to walk in a few before the age of 3. That's for the early late infantile patient. For the early juvenile patient on the right panel, you can see that I don't know if you see my pointer or not. I hope you see it.
Yes, we can see it.
Yeah, okay, fantastic. You have here the course of the early juvenile patient who were treated pre-symptomatically, and you see that you have exactly the same results than for the late infantile patient. And you have here the patient who were treated as they were early symptomatic, and you see that for these patients, in terms of motor function, there is a trend to deterioration, and of course not comparable to the natural history, but clearly the results were less impressive than for the pre-symptomatic patients. What was also important is that in terms of cognitive function, you can see here the curve for the cognitive function. The normal cognitive function is in gray, and you can see that the pre-symptomatic late infantile patient develop nearly normally. The same for the pre-symptomatic early juvenile patient, and also the early symptomatic early juvenile patients, even if results were, for some of the patients, less impressive. The same for the performance IQ and the verbal IQ. So very, very positive results, and clearly this treatment has changed the world of MLD for pre-symptomatic patients. A few words on the second treatment that is currently in a clinical trial is the enzyme replacement therapy trial using intrathecal administration of recombinant enzyme. There was a first trial that started 10 years ago, around 10 years ago. And for this trial, this was a phase 1-2 trial, meaning no efficacy criteria, but a trial aiming at evaluating toxicity and the best dose. And this trial showed good safety profiles and tend to some positive effects in patients who received the highest dose of 100 milligram of recombinant enzyme. With despite a motor degradation, they seem to have some mild better results than untreated patients, and also normalization of the sulfatides that accumulate into the CSF. And because of these results, Shire and then Takeda decided to do a phase 2-3 trial using higher dose, 150 milligrams, and more frequent injection every week instead of every other week. And this trial was and is has for objective to test the efficacy of the treatments. And we have recently obtained the results of this trial, and unfortunately the primary endpoint, that was a purely motor endpoint, was not reached. Whereas clearly I think that all investigators and all parents, of course, who see the patient think that this treatment has some effect. After having decided to stop the trial and propose the treatment as a compassionate treatment in patients enrolled in the trial, finally, recently Takeda decided to continue the trial. And it's a good news, even if we don't have any evidence for the future. And this is clearly a question. And I think that the fact that Shire decided to continue the trial, I don't know exactly the reason, but probably one of the important reasons was that you parents of children involved in the trial, and also with the help of ELA Association, have made a very important work to show to the company that this treatment is not so inefficient that the primary endpoint said. So let's talk now about Krabbe disease, which is a lysosomal storage disease with a deficiency in the galactocerebrosidase or GALC enzyme, leading to accumulation mainly of psychosin, severe demyelination in the central and peripheral nervous system. The most frequent form is the early infantile form. It's a terrible disease with onset, very early onset, before 1 year, but mainly before 6 months. And the first symptoms occur around 3 months with a very rapid deterioration and early death. In these patients, the only available treatment is hematopoietic stem cell transplant, but only if performed in a pre-symptomatic patient. It means that the patient should be treated in the first months of life, which is, of course, very difficult to organize a transplant in such a short period. And additionally, the disease should be diagnosed, and this is possible, for example, in US, in some states where there is a neonatal newborn screening. But of course, in countries where this treatment, this screening is not available, it's more difficult to treat the patient. The late infantile form and other late onset forms, juvenile and adult, have most often slower progression, and hematopoietic stem cell transplant may be considered if they are pre or early symptomatic. These are the results, just to confirm that I said, of the results of hematopoietic stem cell transplant in Krabbe disease. On the left panel, you have the results for the early infantile Krabbe disease for patients treated pre-symptomatically before four weeks. And what we can see is that this treatment, if performed very, very early, may allow positive effect on cognitive function. However, in terms of motor function, the results are not so good, and particularly because of the peripheral neuropathy, and we will see that later. In late onset forms, you can see that the treatment of that hematopoietic stem cell transplant can increase the lifespan and improve the neurological outcome. The results are less favorable once patients are already symptomatic, and most often, like in early onset forms, cognitive and language function are better preserved than motor functions. And just to take a time on this slide, because for me it's a very, very important slide. I say that hematopoietic stem cell transplant may improve Krabbe disease, but it's not enough, and particularly, not only, but particularly because of the peripheral neuropathy. And this was the work of David Wenger and Mohamed Rafi on mouse that are very ill. The mouse model for Krabbe disease mimics the disease. And they have compared the results of hematopoietic stem cell transplants in comparison to intravenous gene therapy using an AAV10 vector and the combination of both treatments. And what was very impressive is that you see here the survival of the untreated mice. You can see that if you treat the mice with bone marrow transplant, you have a better survival, but not perfect, because the mice dies. And it's the same, globally the same, if you do only intravenous gene therapy. But if we combine both treatments, you can see these very nice results in the MLD mice that can survive very, very long in a good health with improvement of motor defect, and also, and this is of importance, prevention of the peripheral nerve disease. And probably that hematopoietic stem cell transplant is not sufficient to prevent the peripheral nerve disease, whereas AAV gene therapy may have a very important impact. And based on these results, there is no clinical trial developed by Forge Biologics. There are in fact two trials, but now they are mixed. The one is a rescue trial, and it consists to treat early infantile Krabbe disease patients that were picked or diagnosed with a newborn screening, and they were treated in the first months of life with first hematopoietic stem cell transplant, and a few days after, a few weeks after, with AAV gene therapy. And there is a second trial for patients who have already been treated with hematopoietic stem cell transplants, even months ago, and that can have an additional treatment with intravenous gene therapy. And that's for either asymptomatic early infantile Krabbe disease, or also for late infantile Krabbe disease with onset between 12 and 47 months, who are symptomatic or post-symptomatic. And we have shown in several presentations that there are very, very promising results for the first two patients who were treated in the rescue study, with preservation of motor and cognitive function, high level of enzyme in the blood and CSF, and also, of course, the safety of the procedure. And I think that this treatment is very, very, very interesting for the future in other leukodystrophies or neurodegenerative disease, just combining two approaches. So in summary, metachromatic leukodystrophy and Krabbe disease are treatable leukodystrophy, but treatment should be initiated before or at the beginning of the symptoms, and most often, unfortunately, patients are diagnosed when symptoms are already present or even advanced. Combined treatment would be necessary, particularly when patients are already symptomatic, And we can, as I said, have a hope that maybe small molecules acting on inflammation or oxidative stress may be helpful in association, of course, with a treatment consisting in giving the gene or the enzyme. Of course, symptomatic treatment is also crucial. And for HSCT, for hematopoietic stem cell transplant in metachromatic and Krabbe disease, leukodystrophy and Krabbe disease, this is a case-by-case discussion, really, because it's not so evident that this treatment may have an effect. And once again, the treatment may accelerate the disease. Of course, familial screening is mandatory when you have a baby, a case what we name the first case in the family, the index case. You should screen urgently the younger or generally the brother and sister, but particularly the younger brother and sister. And newborn screening, as we talked in the previous presentation, of course, will be necessary and mandatory for this disease when a treatment is available. And just to finish, we are now at this time for MLD and Krabbe disease, but it is also the same, and we have heard in the previous presentation for other leukodystrophy, where we are not alone thinking of a patient or what can I do with this patient? Shall I do a transplant? Is there an indication for ex vivo gene therapy? Are there clinical trials and so on? So clearly now there is a community for particularly for MLD, but also for Krabbe disease, and there is this very nice consortium that has been created by the Amsterdam team, particularly Nicole Wolf. And in this consortium, there are a lot of specialists, MLD specialists, and we discuss every case, indication for SHCT, indication for MLD, and so on. It's very, very important. In addition, there is an international disease registry that is currently in construction. Of course, the ELA Association has also a very important role to put the family together with a physician or to put the family together with other family. And in French, we have this reference center for leukodystrophy where of course, we can also see the patients and discuss either in the children in the Kremlin-Bicêtre Hospital. This is my email address. And for adult patients, because MLD and Krabbe is also an adult disease, even if gene therapy for the moment is not available for adults, I put the mails of the reference center at La Pitié-Salpêtrière, led by Fanny Moschel. I think I finished, and thank you for your attention.
Dr. SEVIN, thank you so much. As a reminder, we'll be taking questions for all the talks at the end. So at this point, I'd like to introduce Dr. KLOUWER. Dr. KLOUWER from Amsterdam University Medical Center. Thank you very much, Dr. KLOUWER, for joining us. And she'll be speaking about Zellweger spectrum disorders. I will stay on just to let you know when we see your screen, Dr. KLOUWER.
Yes, give me a moment. I will share my screen.
Yeah. I'll just let you know when we see it so you're reassured that we can see and hear you. Perfect, we can see. Thank you.
Okay. Hello, everybody. So you can see my presentation now, right?
Yes.
Okay, great, thanks. Well, hello, everybody. Thank you for the invitation to speak to you today about Zellweger spectrum disorders. I will give you a brief overview, but mainly focus on the management approach, which is mainly supportive management. My name is Femke KLOUWER. I'm a medical doctor. I did a PhD in Zellweger spectrum disorders, and I'm still part of the Center of Excellence of Proximal Disorders within the Amsterdam UMC. I'm part of the Scientific Advisory Board for GFPD and Zellweger UK, but I have no other disclosures. So first, I would like to give you a brief overview of the biochemical background of Zellweger spectrum disorders and make this, well, complex scheme of proteins and peroxisomal functions to a more understandable concept. I will give you a clinical overview and mainly talk about advices for follow-up and supportive management. and I will briefly talk about the development of a therapy and updates about that. So cell weaker spectrum disorders are caused by variants or changes in one of the 13 PEX genes, and most common are the PEX1 and the PEX6 genes. And those PEX genes, or the PEX proteins, are involved in creating peroxisomes, also called biogenesis, or importing proteins into the peroxisome. And so normally if you stain those proteins, you get this punctate pattern in a healthy control, which are the proteins that are in the peroxisome. And in case of a cell weaker syndrome, the proteins are not imported in the peroxisome anymore, and then you get this diffuse pattern. And because of this peroxisome biogenesis disorder, so the disorder in the formation of peroxisomes, all peroxisomal functions are affected as a result. And because of that, you get, unfortunately, multiple biochemical abnormalities. You get increased very long chain fatty acids, accumulation of toxic bile acid intermediates. You get accumulation of branched chain fatty acids, which are phytanic acid and pristanic acid. There can be a plasmalogen deficiency and also an increased urinary excretion of oxalic acid. Cell weaker spectrum disorders are peroxisomal disorders, and they belong to the group of peroxisome biogenesis disorders, as shown here in the upper part of the screen. And originally, multiple subtypes were described. You had the classic cell weaker syndrome, neonatal adrenoleukodystrophy, infantile Refsum disorder, and the more recently in 2015 described Heimler syndrome, which were all cell weaker spectrum disorders. But nowadays, we actually know that you cannot really divide patients in these categories because it's really a spectrum of disease. Patients can be anywhere on the spectrum. So yeah, you cannot make a clear distinction in these originally described phenotypes based on biochemistry or genetics. There are some exceptions, and that's mainly related to the PEX gene. So you have PEX2, 12, 10, which can have quite a distinct phenotype. And I can imagine that in the future we'll talk about, for instance, PEX16 related disease instead of a cell weaker spectrum disorder. But for now, it's all cell weaker spectrum disorder. So originally, a cell weaker syndrome was described, and those were the patients that were most severely affected. So that was in 1964, and they recognized that these children had typical facial features. They had, unfortunately, quite severe brain abnormalities. There was liver dysfunction and enlargement, renal cyst. And only later it was actually recognized as a problem of peroxisome, so as a peroxisomal disorder. And it was later named cell weaker syndrome to the physician that contributed the first patient. So then symptoms. Well, in principle, all patients have sensorineural hearing deficit, ocular abnormalities, which is mainly retinitis pigmentosa, and teeth abnormalities of the secondary teeth. But the other symptoms really greatly depend on the severity. And you can roughly make three categories of severity based on the presentation. So based on the age of presentation. So children that already show symptoms at a neonatal or infantile age usually have severe hypotonia. They can have seizures. There are neuronal migration defects on MRI of the brain. There's usually quite profound failure to thrive, enlarged liver, but also liver dysfunction, and that causes bleeding problems and the facial features I talked about earlier. Then the children that present in childhood usually have a milder form of hypotonia. They can have a leukodystrophy, and that can already happen at an early age with a sudden onset and a rapid deterioration, but it can also happen at a much later age and with a much slower course. Developmental delay is usually present, and also in these children, hepatomegaly and hepatic dysfunction can occur, but usually less profound. And an important feature to consider is the adrenal insufficiency that can also develop at a later age. Then there's the group that presents at a much later age, can even be adolescent or adult. They can have a developmental delay, but there are also patients described the completely normal cognitive functioning. Neuropathy can occur, ataxia, also again the leukodystrophy, also at a later age and adult age, and also in this group adrenal insufficiency may occur. And it's very important that a physician is actually aware in which group a patient belongs, or roughly belongs, because then somebody can also be aware which problems or symptoms may occur, or which symptoms are very, very unlikely actually to occur. Yeah, then a bit about the facial features. Here you can see a quite severely affected girl, and the large anterior fontanelle is drawn here, which is really big. Also, there's an enlarged forehead, broad nasal bridge. Then a child that presented in a childhood age, already more subtle, but you can see, especially at a bit later age, a broad nasal bridge and also the high forehead, for instance. Then a boy that presented in late adulthood. Here you can see that at a younger age, the facial features were very subtle, but then at a later age, the facial features do become more prominent, and you can notice the high forehead, for instance, low set ears, etc. So about the diagnosis, you can do metabolite screening in plasma and urine. So all these peroxisomal functions we talked about earlier that are abnormal, you can measure those metabolites in blood and urine to establish the diagnosis. So you can measure the very long chain fatty acids that are increased, the bile acids, intermediates, and the branched chain fatty acids, for instance. Then of course the genetic analysis to find the changes in one of those PEX genes. But more and more often, patients are not diagnosed because a clinician thought of a peroxisomal disorder, but for instance by whole exome sequencing, or even as an accidental finding in newborn screening for X-linked adrenal leukodystrophy, which is performed in more and more countries. For instance, in the Netherlands and some of the European countries, they don't look for cell weaker spectrum disorder in the screening for X-linked adrenal leukodystrophy, but for instance in the US, they do. And in these cases, it is of course very important that the diagnosis is confirmed, so also by metabolite screening, for instance. Yeah, then the prognosis I already talked a bit about is of course completely depending on the severity. We know that patients with the classic cell weaker syndrome phenotype usually die within the first year of age, unfortunately. But patients with milder phenotypes can definitely live into adulthood. And there are also rare cases of a normal intellect, which is usually genotype specific. But in all cases, unfortunately, it is by definition a progressive disease. So then about therapy. No curative therapy is available at this moment for cell weaker spectrum disorder. And unlike the previous talks, unfortunately, there are no clinical trials at this moment running for cell weaker spectrum disorder. I will talk a bit about that later, why that is also difficult for cell weaker spectrum disorders. But there are a few supportive treatment management options that are, I think, very important to be aware of, especially as a parent or a patient. And that is supplementation of fat-soluble vitamins, treatment of adrenal insufficiency, of course, hearing aid glasses, a feeding tube, anti-epileptic drugs. But I will go through a few of them. So, fat-soluble vitamins. Low fat-soluble vitamins level, which are A, D, E, and K, are actually very common in cell weaker spectrum disorders, and they can be easily supplemented. This is important because, for instance, low vitamin K levels can cause easy bruising, but also severe bleeding, and a special gastrointestinal tract bleeding might be a problem in patients with a cell weaker spectrum disorder, especially with a bit more severe phenotype. In general, we advise to do a laboratory checkup for the fat-soluble vitamins once a year. Then there are a few dietary management options. You can have a phytanic acid restricted diet, especially when the phytanic acid is high, but it's usually not necessary in cell weaker spectrum disorders, especially not at a later age. For more severely affected patients, a gastrostomy is usually needed, and we no longer advise to have DHE suppletion at this moment. Yeah, then the adrenal insufficiency. About 30% of the patients actually develop adrenal insufficiency, and there are also reports that even report a higher percentage, but it's definitely a problem in cell weaker spectrum disorders. The adrenal glands normally would produce stress hormones, and it's important to notice that some patients can be asymptomatic. Some patients may experience fatigue or nausea, vomiting, low blood pressure, for instance, but they can also be asymptomatic. And you can easily treat it with hydrocortisone, and if you don't, you really can get into problems. So we advise to screen for adrenal insufficiency at least once a year. And of course, those advices are not carved in stone and also depending a bit on the severity and the age. But in general, we screen all patients once a year. So then the liver cirrhosis. We know that a long-term effect of liver cirrhosis, and we know that liver cirrhosis unfortunately occurs in cell weaker spectrum disorders, is the development of liver cancer. And only a few cell weaker spectrum disorder patients worldwide are known to have developed liver cancer, but it's important, of course, to screen for it. So that's also something we screen for every year in case of liver cirrhosis. So the recommendations for follow-up, most important, you need a coordinator of care. There will be a lot of different specialists involved, depending, of course, on the symptoms, but you definitely need a coordinator of care. This can be a pediatric neurologist or a metabolic pediatrician or metabolic specialist, depending on the age, but all those different specialists might be involved. In children, we usually do follow-up every 6 months and every 12 months for adolescents, and you can combine this, of course, with the diagnostic tests. So also, for instance, the abdominal ultrasound to screen for the liver cirrhosis, for kidney stones, and also the laboratory testing, for instance, for the adrenal insufficiency. Yeah, so then a bit about future therapies. Well, future therapies, was very elegantly showing in the previous presentations, is usually go from bench to bedside. So they come from the laboratory, and it takes a while, of course, to take them to the bedside. There are definitely different strategies to identify potential treatments for cell weaker spectrum disorder. I will name a few in the next slide. At this point, most research groups are actually working on different strategies on the same time, because you never know whether a strategy will actually make it in the end from the bench to the bedside. The biggest group working on cell weaker spectrum disorders are the Canadian group and our group in Amsterdam. And also, yeah, both of us are working on different strategies at this moment. And most importantly, it's then still good to realize that when a treatment seems to work in the lab, that's really still something different than a treatment for a patient, and even a treatment that might show positive result in mice is still different than a treatment for patients. Yeah, so then about those potential therapies. Possible approaches for cell weaker spectrum disorders in general might be the correction of the genetic defect, of course. That would be most ideal, although some of the damage might already be done before children are born. But this is actually a difficult approach for cell weaker spectrum disorders because you need a vector to deliver or basically to correct the genetic defect, so to deliver the gene, and the PEX gene is basically too big to put in a vector. So multiple strategies are already used for that, but we cannot, unfortunately, look at other diseases and take that approach for cell spectrum disorders. Then you could try to improve the formation of peroxisomes, so the peroxisomal biogenesis. And we actually already, we and other groups identified multiple compounds that are quite capable of improve the peroxisomal biogenesis in cells. But unfortunately, none of those compounds have proven to be effective in humans yet, but this is definitely a potential approach. You can, of course, try to supplement deficiencies, for instance, the plasmalogens. This has been tried in the past, but it's difficult to let the plasmalogens cross the blood-brain barrier to actually work in the brain, and that's where you need them to work. Then you can try to prevent the accumulation of toxins, for instance, the bile acid intermediates. But of course, this is not an ideal approach because then the other toxins still accumulate. You can only encounter one of them. One of these we have actually tried in a clinical trial before. This was the cholic acid trial, in which by giving a primary bile acid, that is cholic acid, we actually try to suppress the endogenous bile acid synthesis and thereby decrease the accumulation of the toxic bile acid intermediates that the body is making by trying to make these primary bile acids themselves. And furthermore, you can stimulate bile flow by giving primary bile acids, and that might improve actually the take-up of fat-soluble vitamins. But although we saw a biochemical effect, so we saw the decrease of the toxic bile acid intermediates in the patients we treated with cholic acid, those were 21 patients, we did not see any clinical benefit after 21 months of treatment with cholic acid. So we didn't see improvement in growth or fat-soluble vitamin concentrations or liver function, liver cirrhosis. So we don't know, of course, if you would start earlier or maybe would treat longer, this would make a difference. But after 21 months, we did not see an effect. And more importantly, we actually noticed that caution is needed in patients who already had advanced liver disease or cholestasis, because there were actually toxic effects to the liver of the cholic acid if we gave those patients cholic acid. So at this point, we're not treating our cell weaker spectrum disorder patients with cholic acid anymore. So in conclusion, although no curative therapy exists, there are definitely important management options to be aware of in cell weaker spectrum disorder. It might be good to ask your physician about that, or in worst case, even inform your physician about that if they're not aware. And there are multiple strategies to identify potential treatments, but unfortunately no clinical trials are currently running for cell weaker spectrum disorders. And international collaboration is definitely of key importance to achieve that in the end, both in developing therapies, but also in identifying patients, learning about disease, etc. Yeah, just quickly, two patient organizations I would like to mention that can be of help for parents or patients is the GFPD, the Global Foundation for Peroxisomal Disorders, which is based in the US. And also, if you're based in the UK, you have Cell Weaker UK, which is also a big united group of parents within the UK. And I'm very willing, of course, to take any questions later.